So we're going to talk about the product distribution today and how to determine it. Right, so you have a little equation here for determining like the percentages of each product form, right? And it looks really intimidating, but it's not. So let's go through and discuss it. So the N right here represents the number of the type of proton, whether it's, so these two numbers kind of go together, right? Okay, so that'll be the number of the type of proton or hydrogen. One day. All right. It looks intimidating. It's really not. So you got every carbon that's going to be abstractable is going to have hydrogens on it, and it's going to be a type. It's either going to be a primary or a secondary or a tertiary carbon, right? So that's what the NHI represents, like how many primary hydrogens or secondary, depending on what you're trying to calculate, how many primary, secondary, or tertiary hydrogens there are. And then right here, R is a known value. It's a reactivity factor. So that's in the chart. And then what you do on the bottom is you take the sum of everything, right? The sum of each type times the reactivity factor. And so let's do that with this example just to kind of clarify it. And then we're going to do another example. How does this do? 1 second. Sorry about that. That was a dean calling. He always calls when I'm in class. What was I saying? So the bottom number is the sum. So let's look at what we have. So we look at our starting materials. We can see that we have, and let's look at the ones that we have highlighted. Right. So for these hydrogens, well, actually, you know what? Let me just cut this and bring it down, and then that way we can. Sucks. That's all right. We can put the carbons back in. All right. So if you look at the hydrogen or the carbon that's highlighted in orange, this is a primary carbon, right? Because it's only bonded to one other carbon. And then the green carbon is secondary. Can y'all see that? That is bonded to a carbon on this side and on this side, right? So that carbon that's highlighted in green is secondary. And then the purple carbon is also secondary. All right. So when we start calculating the percentages, so the N for primary carbon, let's just say for primary, NHI, it looks complicated. It's really not. It's 6. Right? Even though we're not touching the other carbon down here on the end, it's still abstractable, and so we have to account for it when we calculate the percentages, because that abstraction can happen on either end, right? There's nothing to distinguish one end from the other since it's symmetrical. Go ahead, Tia.
Where does 6 come from?
So you got 3 here. Let me get the right pen. You got three hydrogens here, and oops, that's what this CH3. You got 3 here. So those are the same, right? Since it's symmetrical.
Okay.
Yeah, so you got to count all of them. Right, and then for your secondary, normally I break it up if the the carbons are different. And so let's do that. So let's break that up. So you have for one of your secondaries, the green ones, you have NHI equals 4. Can y'all see that? Because this carbon over here is also identical to the other secondary. Yes, no?
So wait, so first the primary, you saying it only has 1 carbon, correct?
Say that again.
For the primary carbons, you're only saying that 1 carbon is connected, correct?
Yeah, it's bonded to one other carbon, yes.
And then we're looking at symmetry, so you can't count them twice?
No, you do count them twice in the sense of trying to figure out the percentages, because
Okay.
both sides are equally susceptible. So I could do abstraction on either one of these, but I'm going to get the same product.
Got it. Okay.
You understand what I'm saying? So when we're doing the mechanism, we don't have to show them both because you're going to get the same product no matter what. But when we're counting up for the product distribution, we have to understand that both of those carbons can be abstracted. So the abstraction is not going to happen on one end and not the other. So I have to count all 6 of those hydrogens when I'm thinking about product distribution.
Okay.
Like how much of go ahead.
That makes sense.
Yeah. And the same thing with the secondary, the green ones. Let me put that here. All right. The same thing with the green secondary carbons. Those are different from that secondary carbon that's in the middle. So we're gonna count those, even though it's gonna be the same number. We're gonna separate them out because it is a different product, right? When you put a chlorine at one of those 2 sites, it's gonna be different than if you put a chlorine at the purple site, right? And you can see that up here. Let me just bring the products down to where we put them. Let me copy these and put these down here. All right, is that making sense? Everybody okay so far? Do you see that the purple and the green products are different, even though they both end up on secondary carbons?
Yeah.
All right, cool. So then the other secondary, that's purple, or whatever color you want to call it, pink, fuchsia, mauve, it's up to you. So that NHI number is going to be 2. We're okay with that. Don't get thrown off by the NH, all that. It looks like it's something special, but it's really just a number of the type of hydrogen. All right. And then what's going to change though is R, right? The reactivity factor. And the reason that changes is because the stability of the carbon, of the radical that you get when you pull off a extracted hydrogen from one of those carbons is going to be different. A primary radical is less stable than a secondary. A secondary is less stable than a tertiary. And so that's why when you look at the reactivity factor, right, the number goes up from primary to secondary to tertiary, right? The reactivity is increased because the radical itself, once you form it, is more stable as a tertiary. So the radical stability follows the same trend as carbocation stability. All right.
What about the Carbo Anion?
That's the reverse. the less substituted carbanion is going to be more stable than a more substituted. And I can show you that. Just let me finish this part and then I'll write them. I'll put all 3. So radical stability mirrors carbocation stability? That's a great question though. Right? So when you're talking about, let me just put it back here. I'll just put it on the last page. All right, so you have, so for carbocations, tertiary is the most stable, and then secondary, and then primary, and then methyl. Radicals follow that same trend. Tertiary, secondary, primary, and then methyl. And then for carbanions, it's the exact opposite. The methyl is the most stable. And I'm gonna show you why. So the same thing that stabilizes, let's take a tertiary carbocation. 3 bonds to carbon. Come on, Russell. Right? Right. Remember we talked about how this is stabilized by these little dipoles from the carbon-carbon bonds all feeding into the plus charge through induction, or the term I gave was hyperconjugation. Right, that stabilizes that positive. But if I had a tertiary carbon that was negative, it would have a destabilizing effect for the same reason, because the carbon is already charged. Right, so pushing more electron density towards a carbon that's already electron rich is bad. That's why the tertiary carbanion is the least stable of all, right? Because the carbon is already electron rich. So if you're donating more electrons towards it, you're going to destabilize that charge. All right. By the same token, if I have a methyl carbanion, something like this with no carbon-carbon bonds, that's excellent. Right? This is highly stable. Right, so for the anions, the less substituents you have around the carbon, the better. Right, the radical is the same way, because the radical is a half fill. It's a half fill orbital, so it's got a 1 electron instead of 2. So it's looking for some electron density to kind of complete that half fill shell, and so boom, now you want electrons going that way. So since it's half filled, the orbital can accept more electrons.
Are these arrows for induction where you're moving?
Yes. Yeah, it's a type of induction, yes.
Okay, so you're saying for the carbo anions, you wouldn't want the electrons going towards the more negative side?
Nope, because it's already electron rich. It's already got a pair of electrons on carbon, so you don't want to give it more electrons, because that's not good. That'll destabilize the charge.
Okay.
Remember the goal, even though this is a totally different concept, the idea of delocalization is always important, right? You want that charge to be delocalized, not centralized and then intensified by more electrons being donated to it. you want to be able to spread that charge out. So with the positive charge, the fact that it's empty, then yes, it's hungry for electrons. So you want those electrons going in that direction. But with the carbanion, that p orbital is not empty, right? It's got a pair of electrons in it. So you're going to, any more electrons you push towards it would destabilize it. All right. Did that answer the question? I think, was that you, Tia, that asked that?
Yes,
All right. Is it clear now?
yes.
All right, cool. All right, let's go back up to our example. So we got all these numbers, and now we can apply. All right, we can apply this equation. Let me make that a little bigger, because that's going to be tiny when I upload this. Come on, Russell. It's just been a rough morning. All right, so now we can apply the equation. All right, so let's take, for primary, since we're working with chlorine, right? That's our halogen. The R value is going to be 1 for chlorine. And then for primary, or secondary is going to be 3.9. And then tertiary is going to be 5.2. All right, so let's take that value, and we're just going to let's do the denominator first, because once we do that, we don't have to do it again. So we got 6 primaries, and then times 1, right? Because R is 1 for a primary carbon with chlorine. Yes.
Wait, can you say that again?
So we're working on this NHR part right here. So we know what NH is. We got 6 primary carbons. 6 primary hydrogens, 4 secondaries, and then another 2 secondaries on a different type of a different carbon, right? So for the primary, let me just keep the color scheme the same. Right, it's going to be 6 for the number of hydrogens times 1, which is the R value for chlorine and a primary carbon. Is that right?
Yes.
And then the other number for secondary, R is 3.9. So we're going to do 4 times 3.9. And then we got the other secondary, we're going to do 2 times 3.9. Right. Once we get that sum at the bottom, we won't have to recalculate it. So that's 6, that's 15.6. And then that is 7.8. So 6, 15.6, 7.8. That's going to be 21.6. It's 29.4. Is that right?
So whenever you get those 3 different numbers, you're just going to add them. You're not going to multiply them together.
Yeah, it's just a sum. That's what the little sigma out here represents.
Okay.
Yeah, it's just a sum of all of them.
I got 29.4.
Okay. All right. So that's my bottom number. So now for the primary, let me just see if I can just copy this. So for primary, I can just stick those numbers in. So the top number is going to be 6 times 1, right? If I'm doing primary. So let's do that. So it's going to be 6 times 1, where 6 is the number of primary hydrogens. And then 29.4 is the sum that's going in the bottom. All right. We're okay with that? All that is the top, the NHI R is whatever it is for that set of hydrogens, right? So it'll be 6 times 1 over the total times 100. And then for the secondary, it's going to be the green ones, 4 times 3.9 over 29.4 times 100. And then for the other secondary, let me move that down some. It's going to be 2 times 3.9 over 29.4. Y'all following? And it should add up to 100%. That's what we're calculating, is the percentage of each product. Anybody got the primary calculated yet? It's gonna be somewhere around 19 or 20%, isn't it?
20.7%.
20.7. All right, so this is 20.7%, good. And then this one is gonna be close to 50, isn't it? 15.6 divided by 29.4, might be a little bit over 50.
53.
53%.
53.1.
Okay. And then the other one has to be make this add up to 100. So it's the 73.8. So it should be 26.2. Is that right? Somewhere up in there.
26.5.
Was it 26.5? So one of these.
One of them was over, I guess, because of rounding.
Okay. All right. So that's how you would calculate those percentages, right? The key is to understand what those terms mean in that equation, right? So the NHI part is going to be the number of hydrogens, and then R is going to be the reactivity factor. So let's see what happens if we take the same molecule, but instead of chlorine, we use bromine. Actually, or y'all want to do a different one? I can't remember which molecule we did in the video. Was it bromine or chlorine?
Bromine.
And it was on something like this, wasn't it? Something like that. So let's do this one. Let's do it with chlorine though, and light. All right. So let's look at, so this is not symmetrical, right? The only part that's symmetrical is going to be here, these two carbons. But everything else is going to be fair game. So you got to put one here, 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 and then here. All of those are going to give you different products. All right, so we can go through that mechanism, and we can go through and figure out what's primary, what's secondary, and what's tertiary. Right? So each one of these is a different type of carbon, right? Where are my primary carbons?
On the ends.
The terminal ones, right? That's primary, and then this is primary. And then you can see also the pink one is tertiary, right? Because that carbon is bonded to 3 other carbons. Can y'all see that?
Yes.
All right, and then this is secondary, and that's secondary. All right. So we're going to do it the same way. We're going to break up the secondaries, even though they're both secondary. We're not going to lump them together because they're going to give us 2 specific products, 2 different products. So let's draw the products first. And then what we're going to do is go through the mechanism just to get a more reps with doing that initiation and propagation and termination. And let me fix that.
So the second and the fourth carbon, they aren't the same because one is tertiary, correct?
Second and the fourth carbon, help me out. Talking about the pink one and the brown one,
From the right side, the yellow one and the
yellow and green.
the pink one.
Oh yeah, definitely. The yellow carbon is secondary. The pink carbon is tertiary. You can see it's got a carbon bonded to here, here, and here that are all bonded to this carbon right here. That's why it's tertiary.
Okay, so you wouldn't consider their symmetry the same because of that?
Yeah, no, it's not symmetrical. Yeah, it's not symmetrical. Like you couldn't put a mirror plane through this molecule anywhere except here. Right. So that's why I colored those 2 primaries. They're the same because they are symmetrical. Because they're on the same carbon. And regardless if you put another atom here or here, you're going to get the same product like the isomers. And actually, we can talk about isomers now a little bit when we draw the products, because that'll help it to make more sense. All right, so let's put a chlorine here. This is going to be one of my products. All right, we're going to get a chlorine here. We're going to get one here. And we're going to get one here. Like that. Everybody following? Anybody not see it?
I have a question.
Go ahead.
Wait, can you go up? Can you go up?
Up.
Oh, never mind.
You sure?
Mm-hmm.
All right.
I was gonna ask, where'd you know where to add the chlorides?
All right. So when we went through and identified all the different carbons, remember all of those carbons have hydrogens on them. And if this is a radical substitution, anywhere that there's a hydrogen that can come off or be abstracted, you're going to end up with a chlorine there when you get to your termination step.
Okay, got it.
Yeah. So anywhere that there's an extractable hydrogen, you're gonna put a chlorine there when it's terminated, because that in propagation, every site that can be abstracted is going to get abstracted. All right, so let's do this, and let me. I forgot to put this other. I'm gonna do these 2 products. I'm gonna show both, even though you're only going to get one, but I'm showing it for the sake of talking about the isomerism. So one of these, I'm going to end up with a chlorine here. One, I'm going to end up here. These are the same though. Right? So let's name them. So I'm going to start at the end where chlorine is. I'm going to start counting right there. So this is 1, 2, 3, 4, 5. And then this is 1, 2, 3, 4, 5. What's my parent if it's 5 carbons? Is it pentane?
Yes.
Mhm. Where are my substituents? And this is,
First,
go ahead.
first carbon.
Okay, I have a substituent at 1. I have a chlorine at 1, right? And what about 2? Don't I have a group out here
You have
that's
a
not a
brand.
part of the longest chain?
Yes.
Mhm. So that's we call that what? A methyl? Is that right? Because it's a CH3.
What was the alkyl? Because I was gonna say alkyl.
Well, that alkyl is a generic name for it,
Okay. Okay.
but the specific name is methyl. It's a methyl group. All right. So we're gonna put this in alphabetical order, right? We have a chloro. And then we have a methyl. Right? So we're gonna put it in alphabetical order. So this is 1 chloro, 2 methyl. Let's see, now I'm gonna run out of room. Pentane. Following? Anybody not see it? Do you see how they're both the same? 1 chloro, 2 methyl pentane. No matter if I put the chlorine on the top carbon or the bottom carbon. Are we following?
Yes.
All right, let's name the rest of them. We're going to start counting from this end because this end has the closest branch point. We know that pentane is our parent. What would this one be? Alphabetical order. This is a CH3.
3 chloro, 2 pentane.
3 chloro. Sorry about that. 2 methyl pentane. Good. All right. What about the next one? You got a chlorine here. You got a methyl group here. I probably should move these around to make room. Let me do that. All right. What about that one? We can count from either end on this one, but we're going to start counting here because chlorine C comes before M in the alphabet. Because your 2 substituents are equidistant. So we're going to count from the end where the chlorine is because C comes before M. All right. What is the name of that compound?
Is it 2 chloro, 4 methyl pentane?
Yes. 4 methyl pentane. Good. Excellent. What about this one?
One chloro, 4 methyl pentane.
Running out of space, and I don't like that. That's all right. I'm gonna squeeze it up in here some kind of way. I'm gonna move that up. Shrink it a little. So this is 1 chloro. Steal that. 4 methyl. And I know this is an aside, but it's a good aside to take. Pentane. All right. Everybody okay? We all still on the boat? Got
Yeah.
one more name. Go ahead. So we're gonna do this one. 1, 2, 3, 4, 5. You can see that. Where are my substituents in that case?
1, 2.
This is a methyl group, the chloro group. They're both on carbon 2. Is that right?
Yes.
So this
Yes.
equals 2 chloro, 2 methyl pentane. See how they all have different names? Totally different compounds, but they all have the same formula. Same formula, different molecular structure. These are all what you call constitutional isomers. They have the same molecular formula, but they have a different structure. Right, same formula, different structure. All of them are what we call constitutional isomers. C6, my bad. C6H13Cl. I'm tripping because the formula for an alkane is CnH2n plus 2, where N is the number of carbons. So if it was C6H14, but the fact that you added in a chlorine, then you have to subtract 1 from the reference. So it'll be C6H13Cl. My bad. I was thinking pentane in my mind, but there's obviously 6 carbons here. All right. So the backbone is pentane, though. Don't lose that. But the overall formula is C6H13Cl. So you can see here you got 1, 2, 3, 4, 5 different ways that you can express that or draw that. And they're all what you call constitutional isomers. Same formula, different structure.
So if you were to give us, I guess the formula, the overall formula,
Mm-hmm.
recommend us to like, I guess, draw out the skeletal form and see if, and then name them to see if they're constitutional or the same.
Well, if you drew out the skeletal forms, you wouldn't have to name them because you would see the differences. Like if you just had C6H13Cl, then when you draw out the isomers that you can get from that, because these are not all of the isomers that you can get from that, because obviously you can have a hexane with a chlorine somewhere on it, right? You can have a hexane there, a chlorine there, right? These are just some of the isomers that you can get, right? There are multiple isomers you can draw. If you drew just a straight 6-member chain, you can put chlorine here. You can put it here, right? So those are just some of the isomers. But the point I was making in naming them is to show that these two products that you're going to get from here and from here are going to be the same, right? So if you name it and the names are identical, then you know that that's the same compound. So because every time when I teach this part and those 2 methyl groups are there, somebody always asks, is that going to be are those 2 different products? And the answer is no, right? You'll get the same product no matter if you substitute at the top primary or the bottom primary on that the branch group right there, because it's symmetrical. That was the whole point of going through this.
So if it's if the symmetry is like correct, then you don't have to worry about drawing those 2 forms. You only have to draw 1.
Yes. Right, but the whole idea behind the constitutional isomers is just to show you that you can have you're going to get multiple products and they're all going to be different, right? With the exception of that branch group where it's symmetrical. Everything else is different. That's why I highlighted all the carbons in different colors, because to indicate that you're going to get different products each time. All right. So we'll work through this on Friday. I may group y'all up and let y'all work on it for a few minutes, and then we'll come back and work on it together as a group. But yeah, we're gonna pick this back up on Friday. So we see all the products. We know what the start material is. We just need to go through the mechanism, the initiation, propagation, and termination steps for this. And then we're gonna also incorporate the product distribution, figuring out what the percentages are of each product that you're gonna produce. So yeah, we'll stop right there. We gotta chop this up, so it'll be a minute before I upload it, but it will be uploaded today because I don't have lab at 1. Because those of you who are in the Wednesday lab, you need to take that midterm. If you were in the Tuesday lab, you had to take it yesterday by 11:59. So today, if you're on Wednesday, you need to take that midterm by 11:59 tonight.